Okay, thank you, and good morning, good evening, good afternoon to everybody, wherever you are. I'm not actually in Oxford, but I'm based in California now, where it's a balmy 28 degrees outside. I'm going to be giving some personal reminiscences of the development of conformal field theory since I started in that field in the 1980s. And unlike some of the other speakers, I'm not going to be writing lots of equations. I'll just be talking about the subject in a rather general way, and and because this is because conformal field theory is a huge subject, I'm going to concentrate on its applications in condensed matter physics, only mentioning string theory and other things as part of the historical context. And so it will inevitably be subjective, and at some points I'm just going to have to oversimplify what is, as you realize, a very complex subject. So I'm going to start with some background on the context of conformal field theory in terms of quantum field theory in general and the ideas of the Renormalization Group. I'll then talk about why conformal field theory in particular is important in this context. I'll talk about what I call the prehistory of conformal field theory before the 1984 paper of Halyavin Polyakov homologic. I will talk about BPZ and all that. I'll then go on to some of the later developments in the 1980s, modular invariance on the torus and the ADE classification of two-dimensional critical behavior. I'll talk about boundary CFT and conformal boundary states, and then I'll go on to more applied things. Both I'll talk about random planar curves and their relation to conformal field theory, which sparked a whole development in mathematics called Schramm-Loevner evolution. I'll then talk about some applications in physics, about quantum entanglement, about quantum quenches, and I will have missed out a huge amount, and I will end there. So let me begin by talking about the unreasonable effectiveness of quantum field theory. And of course, this is a misquote of a famous quote of Eugene Wigner, who talked about the unreasonable effectiveness of mathematics in physics. Well, the thing about quantum field theory is it gives us a framework, a language in which to talk about many different things in physics. Although it was originally developed as a theory of the electromagnetic interactions, and then it was extended through the weak and the strong interactions, and it became this marvelous structure called the Standard Model. It's certainly by no means the preserve of particle physics. And one of the contexts in which that's understood is the fact that the Euclidean path integral bears a strong mathematical resemblance to classical equilibrium statistical mechanics, where you would typically have a lattice or some short distance cut off, and then it would be more appropriate maybe not to call it quantum field theory but statistical field theory, and in fact that term has become quite common, and there's just certainly been a marvelous example of the symbiosis between different branches of theoretical physics, where ideas that were developed in high energy physics have been applied in statistical mechanics, and you have the marvelous example of lattice gauge theory as being a way of formulating for example QCD. So if you look on the archive, in fact, you will see that the number of papers that use quantum field theory ideas in condensed matter physics nowadays is at least as many as appear in high energy. And in fact, quantum field theory, or maybe I shouldn't call it quantum, I should call it statistical field theory, can be applied to just about any system with many interacting degrees of freedom distributed in space. And and there are examples where it's applied to turbulence, to the spread of infectious diseases, to economics, to all kinds of things in the social sciences too. And this, I would like to suggest that the essential common feature of these applications is some kind of stochastic averaging on local fluctuating fields, which inside correlation functions obey some kind of an OPE. And that is the essential feature of a quantum field theory. And the other essential feature is that these OPE coefficients, the CRJKs, can display anomalous behavior, that they don't necessarily scale with their engineering dimensions. Of course, the other thing about quantum field theory is that it's spun off many new ideas into mathematics. And there are lots of examples, and I will quote a couple of these as I go on in my talk. So Renormalization Group. This is a terrible name. It's not a group, it's a semi-group, if that. It was originally used in the context of renormalizable quantum field theories, where you're talking about a very simple flow within a particular renormalization group trajectory, but then it was reinterpreted or explained by Ken Wilson as really something that takes place in, quote, the space of all possible ultraviolet cutoff quantum field theories. Now, this space is a global concept, and we really don't have a good mathematical description of it, but we can do a lot of approximate calculations. We can do all kinds of things with this Wilsonian idea. And the important thing that comes out of this is that it's the fixed points of the renormalization group which are going to become important. And these correspond to scale invariant field theories. And in the vicinity of a fixed point, you have an inflow and an outflow. And typically the outflow is a finite dimensional manifold spanned by the infrared unstable, or what we call the relevant couplings to scaling fields with a dimension less than the dimension of space, and it's these that we would normally call a renormalizable quantum field theory. And they typically, when you turn them on, generate a non-perturbative mass scale in the theory. And then there's an infinite dimensional co-manifold of infrared stable or ultraviolet unstable couplings to fields of dimension greater than d. And but as long as those couplings are small, they can be treated perturbatively in the context when we're trying to look at infrared physics, as in StatMech normally. They give you what are called corrections to scaling. In the context of high energy physics, they can be treated perturbatively, and they give you the kind of effective field theories that we've been hearing about. But the important thing is that if we just want to know what are the scaling fields, what are the scaling dimensions, and the correlation functions, we only need to know information about what's going on at the fixed point. We don't need to understand the flows away from there if we just want this limited amount of information. And at the fixed point, the thing is we have a conformal field theory in general. Thus, Wilson set us the task, no small task, of classifying all such fixed point field theories, computing their spectrum of dimensions, as well as all the other universal data there, the OPE coefficients and the correlation functions, and determining the non-perturbative flows in between these fixed points. So there's this whole space out there which describes the whole world. and there are flows in between these fixed points, and 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 right now all we can do is look at the ones which to us seem to be important and try to understand them and classify them. So conformal symmetry. So even if we start with a lattice or something like that at or near these fixed points, these correspond to irrelevant perturbations. So we have continuous translational and rotational symmetries as what in the modern language we would call emergent properties. It may be that we start with them anyway, but they're often emergent. Not always. There are lots of examples of critical behavior where either translational symmetry is broken or rotational symmetry, and then we get a different kind of massless field theory. It's not a conformal field theory now. However, I'm going to assume that we do have translational and rotational symmetries, and also that the theory is sufficiently local that we can talk about a local stress energy in the StatMech language, or the energy momentum tensor in the particle physics language, which is formally defined as the response of the action to a change in the metric. So actually, this is what's called the improved energy momentum tensor. It's the thing which would appear on the right-hand side of Einstein's equations. It may differ by total derivatives from the Noether current that we would get corresponding to these translational and rotational symmetries. Excuse me. So these symmetries imply that it's conserved and symmetric, and if it's scale invariant, it's also traceless. And it turns out that this also buys us invariance under a wider class of symmetries, which correspond only locally to translations, rotations, and scale transformations, but where the rescaling parameter actually depends on space, and these are the conformal symmetries. More generally, we can think about theories on a curved background. So we can either talk about conformal symmetries operating either in R to the D or R to the supplemented with the pointers infinity. But more generally, what conformal symmetry does is relate what happens in a given fixed metric to one in a conformally equivalent metric. So in statistical mechanics, we always think of the metric as being fixed, and we usually think about it being flat. Anyway, which I'll mention is one of the differences between that and when one is talking about a string theory interpretation. So the pre-1984 history, of course, a great deal had been done about conformal invariance before 1984. In fact, in terms of classical field theory, this goes back at least to 1909 and 1910 when it was discovered in terms of the vacuum Maxwell's equation, and then it was extended to quantum field theories in the 1960s. But there was this important paper by Polyakov in 1970 when he suggested that critical points in StatMech corresponding to massless field theories should also exhibit conformal symmetry. At that time, he also proposed that conformal bootstrap, where he talked about imposing crossing on the 4-point functions evaluated using the OPE, and I'll mention that at the end of my talk. But at that point, this was really looking a long way into the future because the mathematical machinery was not there at that point to actually realize this, even in 2 dimensions. Now, parallel to this, there was a huge amount of work in statistical mechanics inspired by the exact solutions of Baxter, and then more approximate ideas using Coulomb Gas Methods of Dennis and Nienhuis. And they predicted a lot of what came out of BPZ in 1984, but they weren't rigorous, or they weren't even systematic. There was a lot of guesswork involved, and but it was interesting that there were these results out there in the 1970s, even though they weren't necessarily referred to by people working in conformal field theory. So I'm going to talk now very briefly about the Virasoro algebra. It turns out that if you're working in more than 2 dimensions, that the algebra of conformal mappings in flat space is a finite dimensional algebra. But we know that, of course, that in 2 dimensions, any complex analytic function gives us locally a conformal mapping. And the algebra of these infinitesimal generators, although it's known in physics as the Virasoro algebra, was in fact first written down in 1968 by Alfand and Fuchs, including the central term here. So the central term has a coefficient C, which is a C number, and it measures the amount by which the stress tensor fails to transform as a tensor density. And that's a very mathematical interpretation, but as we will discuss, it manifests it manifests itself physically in many ways, and it can be even experimentally measured. The other important thing about a conformal field theory is that we have this amazing thing called the operator state correspondence. In a normal quantum field theory, where we construct the Hilbert space by quantizing on a constant time hypersurface, in a conformal field theory, we can do this thing called radial quantization, where we quantize on the surface of a sphere, and the Hamiltonian, which is really the generator of scale transformations, acts on that and changes the scale. And if we then imagine that we put an operator at the center of the sphere, that's going to create a state on the surface of the sphere. So there's this one-to-one correspondence in a conformal field theory between the operators of the theory and the states of the Hilbert space. And this is a very useful correspondence. It means that the scaling fields, that's the operators of the theory that transform simply under scale transformations, they fall into highest weight representations of the Virasoro algebra. I ought to have mentioned that there are in fact two Virasoro algebras, because once one writes the equations down, they decouple more or less into a holomorphic part and an anti-holomorphic part. So one should really think of 2D conformal field theory as taking place on C2 rather than R2 or C1. But then you need to project down, or specialize rather, into R2 or from that. But it's useful to think of the fields of the theory as depending upon a complex coordinate Z and its conjugate Z bar, and to think of these as independent coordinates. So the Virasoro algebra, as I've said, it appeared in physics in string theory. And in string theory, the conformal symmetry appears because it appears as a gauge freedom of the theory. If you have a certain configuration and padding of the worldsheet in the target space, then conformally equivalent descriptions of that give you the same configuration of the string. So it's the gauge freedom, and whenever you have a gauge freedom like that in a theory, you have to be very careful about how you quantize it, of course, and that was, of course, done very carefully in this paper of Goddard and Olive and Goldstone. And maybe I've forgotten an author there. I apologize if I have. So In string theory, though, one is generally interested in some large value of the central charge corresponding to the number of dimensions that in which the string theory is consistent, and that would be 26 dimensions for the bosonic string and 10, of course, for the fermionic one. On the other hand, if we're thinking about statistical mechanics, the theories with smaller values of C, in particular C less than or equal to 1, are much more relevant. And the reason for that is that as you increase C, you increase the number of relevant scaling fields. And in statistical physics, the relevant scaling fields have to be tuned to the fixed point for you to get critical behavior. And so in a typical experimental setup, you only have the freedom to tune, for example, the temperature and the magnetic field or something. Unless something special is happening, like there's an extra SU2 symmetry or something like that, the theories with C larger than 1 are not particularly physically relevant. So it's interesting that the representation theory of the Virasoro Algebra for C less than 1 before BPZ came along had been worked out by the mathematicians, in particular Huygens and Fuchs and Victor Katz. So now I go on to BPZ, Beliveau-Polyakov and Homologikov. I say 1984, but in fact the preprint appeared, or I first saw the preprint in 1983. So, but I like the choice of 1984 because, of course, that year has other connotations in terms of George Orwell and that kind of thing. So BPZ showed that there are discrete rational values of C smaller than 1, and really this goes back to the work of Katz. And for these particular rational values, the highest weight representations contain null states. That is, states whose scalar product with themselves is 0. And of course, in a unitary field theory, we're also going to talk about non-unitary theories also. You should just set them to 0 or just mod them out. And then that implies discrete allowed values for for the dimensions of the scaling fields. But the important thing that BPZ did was that they showed that this implied that the correlation functions of these particular scaling fields obey linear partial differential equations of a Fuchsian type. And if you then consider these particular models, which are called the minimal models, and you then impose the conformal bootstrap, you have so much extra structure there now that it becomes a finite system, and the OPE coefficients may be determined explicitly. So for all these models, the minimal models, one can compute all the correlation functions in flat space. So then around the same time, I think what had happened is that Dan Friedan had spent some time in Moscow, and he talked to these people, and Friedan, Chu, and Schenker imposed unitarity on the representations of the with c less than 1, so that then selects a subset of these minimal models. And I should say that unitarity in this context is expected because if you have a statistical mechanics model with positive Boltzmann weights, and all of this sort of goes back to the Osterwalder-Schrader formulation of quantum field theory. Then you expect as a field theory, it's going to be a unitary one. So models with positive Boltzmann weights, as you normally expect in a stat-mech model, are going to correspond to unitary conformal field theories. And what people were able to do in 1984 was to show that the first few models in the FQS classification corresponded to well-known stat-mech models like the Ising model and the three-state box model, and so on. And in fact, coincidentally, at the same time, Andrews, Baxter, and Forrester, extending earlier work of Baxter, produced models where they were able to compute the scaling dimensions, and these models were then interpreted by Hoos as being physical realizations of these unitary conformal field theories. There's a very important paper around the same time by Dotsenko and Fatev, who looked at the solutions of the BPZ differential equations. And so, because these are of Fuchsian type, one expects the solutions to be some kind of generalized hypergeometric function, which we know have integral representations. And they showed basically, by extending the Feigen-Fuchs representations of the Virasoro algebra in terms of harmonic oscillators, they showed that the correlation functions themselves could be expressed in terms of exponentials of a free field with a so-called charge at infinity and additional screening charges, additional exponentials floating around. And interestingly enough, the scaling dimensions that one gets out of that then agree with these earlier Coulomb gas conjectures that have been made. The problem with this construction is that it looks non-unitary. There are square roots of -1 floating around all over the place. And so, although one has found a physical realization, it took people a lot of time before they understood what was really going on in this Feigen-Fuchs construction. And the answer was that there's a quantum group in there, which allows you to shrink the Hilbert space down to this unitary sector. And that's a whole different ball game that I'm not going to be able to talk about. But interestingly enough, in 1985, Goddard and Olive, who've been thinking about these Kac-Moody algebras based on a higher Lie algebra symmetry, showed that if one had one with an invariant subalgebra, so you could think about cosets, then they came up with this coset construction, which gave an explicit realization of the FQS series of unitary models, which really showed that these things do exist. So my own journey. Let's see what I'm doing. Okay, I'm doing well. So now I get sort of. So I studied at Cambridge. I was a couple of years behind Peter Goddard. I was a contemporary of John Ellis, for example. And I did a first postdoc at CERN from 1971 to 73. And of course, that was an amazing time at CERN. It was when they were doing interesting experimental physics, both at CERN and elsewhere. And the whole theoretical thing was S-matrix theory had, as has been explained, had been overtaken by the two resonance model and string theory. But string theory itself, as a theory of the strong interactions, was rapidly getting supplanted by QCD, and of course we had the Weinberg's alarm model. A tough was there, and Veltman, and it was a very exciting time. Unfortunately, I wasn't involved in that, partly because at that time the CERN theory group was like at least 100 people, and when you arrive there as a fresh postdoc, it's really, at that time, it was really hard to find people to work with. I worked on something called region field theory, which is a kind of emergent theory of diffraction scattering, which was very, very interesting. But in the end, it doesn't describe diffraction scattering at accessible accelerator energies. So, and in fact, the actual field theory is nowadays reinterpreted as something called directed calculation. This was something I did a bit later, and directed percolation is a fundamental theory of non-equilibrium phase transitions, and in fact it's now been experimentally achieved. So actually region field theory has been confirmed experimentally, but in a different context. Anyway, through studying this, there was a number of people based at Fermilab, Barbanel and various other people, and also Sasha Hegdal. I think he talked about this earlier, where they were doing the epsilon expansion and the Wilson Renormalization Group on this particular theory. And so I got involved in that, and then I had to read all these papers of Wilson and Fisher, and when I joined the faculty at Santa Barbara, that was in 1977 or something, I began to apply field theory ideas to problems in condensed matter physics. Of course, I was by no means the first person to do this. And I remember one colleague who should probably been nameless said, after all, there's only one standard model, whilst almost any field theory that you care to write down has a physical realization somewhere in condensed matter. So another interpretation of this is, why should you get married and just have one wife when you have access to the whole of the world? Yes, I should say that eventually I did settle down, and I've been very happily married ever since. Anyway, in 1983, I was at Santa Barbara, but I attended the big statistical physics conference in Edinburgh. So the BPZ preprint was out, but BPZ themselves were not allowed to travel. But Tarsenko, one of the Tarsenko brothers, reported on the work of APZ. And I remember being in the audience and everybody staring at the results in amazement. Here they were computing all these critical exponents that only people like Baxter and so forth have been able to do even partially. But not only that, they were computing all the correlation functions too. But in that statistical physics audience, I doubt that many people actually followed their arguments. However, all those endless seminars on string theory that I sat through in Cambridge and at CERN finally bore fruit for me, and I was able to get the gist of their arguments. And I went back to Santa Barbara, resolved to thoroughly understand the BPZ papers and to try to work on it myself. So, but the first thing I did was, and I can only do this because I was just in the right place at the right time. I realized that that people who had numerically studied critical two-dimensional models often do so by putting the theory on a cylinder, that is an infinitely or very, very long cylinder, but of circumference L. And that's then a quasi one-dimensional system, so it has a finite correlation length, and you can easily compute numerically the correlation length along the cylinder, because it's what we call a transfer matrix calculation. And according to the theory of finite-size scaling, if the model is critical, then there is no scale in the problem. So the correlation length along the cylinder should be proportional to L, because that's the only scale in the problem, times some universal coefficient. But what was observed numerically is that this universal coefficient is 1 over pi eta, where eta is the critical exponent governing the decay of the two-point function in the plane, not on the cylinder. So this was a puzzle. But the correlation length being L over pi eta is, if you think about the Hamiltonian, which generates translations along the cylinder, you can think of that direction as being imaginary time. This statement is equivalent to the statement that the gap of the Hamiltonian goes like 1 over L with a coefficient 2 pi x, where eta is 2x, and x is the scaling dimension of whatever operator you're talking about. But of course, the cylinder is conformally equivalent by this exponential transformation to the plane, or rather the punctured plane. And translations along the cylinder are equivalent to scale transformations in the plane. In fact, one can argue that the entire spectrum of the Hamiltonian on the cylinder is just 2 pi over L times the spectrum of scaling dimensions of the theory. So then the remarkable thing is that for many models, this 1 over L scaling, which is theoretically just asymptotic, works in fact for L being just a few lattice spacing, where the Hamiltonian or the transfer matrix is just a finite dimensional matrix, which can be diagonalized easily, or there are certain models where one can find the spectrum analytically using the beta ansatz. So this gives a very powerful method, because although FQS had in principle said what are the possible values of the scaling dimensions, that analysis doesn't tell you which particular statistical mechanics model corresponds to a particular conformal field theory. But by doing this very simple numerics, one can immediately identify what conformal field theory is appropriate to the particular StatMech model. And the ground state entity, we ought to have covered this earlier, but there was an interesting simultaneous discovery by my colleagues and I, and also Ian Affleck, that it's actually minus pi c over 6L. So it corresponds to the central charge. And therefore, you can also experimentally or numerically measure the value of C. In fact, if you think about the periodic cycle around the cylinder as being inverse temperature, and the direction along the cylinder as being space, and what you really have there is the path it's a finite temperature path integral for a one-dimensional quantum system, and so interpreting 1/L as being the temperature, you can show that this means that the specific heat of this critical one-dimensional quantum system is linear in the temperature. And this is basically the one-dimensional version of Efan's law for black body radiation, which would say that the specific heat would behave in 3 + 1 dimensions as T cubed. And the coefficient would then tell you the number of polarizations of the electromagnetic field. Well, in one dimension, it's proportional to the central charge C. And so we can see that really what C is doing is counting the effective number of low energy degrees of freedom of the theories. So it has this very elegant physical interpretation. So in 1986, I was trying to understand how I might compute the partition function on the torus. And incidentally, just for historical curiosity, this was the first manuscript I prepared in TAC. What one had to do before this was one got the secretary to type out the manuscript, and one wrote in the equations by hand, and then they were typeset by the publisher with lots of errors. So this was a huge improvement, writing it in TAC, and it was particularly appropriate for this particular paper because it had some rather long equations in it. So if we talk first of all about what I would call a rectangular torus, which is that we take an L by L prime rectangle and we identify opposite sides. And because we know the spectrum, so this is basically a cylinder, a finite cylinder, where we identify opposite ends of the cylinder. And because we know the spectrum on the cylinder is 2 pi xj L prime, 2 pi xj over L, we can compute the partition function on the torus just by taking a trace. Well, that's all very well, but this doesn't look like it should be invariant under interchanging L and L prime, which it has to be. I'm asked, why does it have to be? Well, if I think about this conformal field theory as being the scaling limit of the stat-mech model, it certainly has to be, if it's isotropic. And you can think about the path integral, but if you don't want to do that, you can just impose it as an axiom of conformal field theory. Anyway, it's not obviously so, but of course we know lots of examples of functions like the classical Jacobi theta functions, which have a similar kind of property. So it must be that something has to work out. But before we do that, if we're interested in the limit where L prime over L is quite small, then we have to take a large number of states into account. And in that limit, we can replace the sum by an integral over the density of states. And then by this L goes to L prime symmetry, we know it has to behave like this. And the only way it can do that is if the density of states increases exponentially with the energy, like e to the constant times the square root of x. So this is a very interesting formula, sometimes called the Cardy formula. And what we can see from this is that, well, if there are no null states, then basically rho of x is related to the number of partitions of an integer, and those from classical number theory, like Hardy and so on, that this would grow in the same way, but with a c equal to 1. So for c smaller than 1, each irreducible representation is growing like this. And the only way that could be consistent with an overall growth like this is if there are null states. And that then implies BPZ, FQS, and so on. And it also tells us that for C larger than 1, there must be an infinite number of Virasoro Algebra weight representations. Now this formula here, as well as being valid for large X of fixed C, turns out to be also valid for large C, which is the limit in which one has the ADS CFT correspondence. And then it was argued that this growth of the density of states here is related to the entropy of a quantum black hole in the ADS space-time, which is certainly interesting, but I certainly wasn't thinking about black holes at the time. So more specifically, because the states are organized into highest weight representations of these two Virasoro algebras, it can be expressed in terms of what are called the characters of the algebra, and it's going to be bilinear in terms of those, with some coefficients which, for a unitary theory, are going to have to be non-negative integers. And Q is the modular parameter of the torus. For the rectangular torus, it's just this. But if you replace the rectangle by a parallelogram, then you get non-zero momentum entering, and it's a complex parameter. So what I worked out in 1986 was that these characters in fact give a finite dimensional representation of the modular group. Now, I have to admit with some degree of embarrassment that at that time I didn't realize that was what I was doing. I was working alone in Santa Barbara. I was just trying to understand how this thing could be invariant. And it took other people to point out to me that I had shown that the characters give a representation of the modular group. To my embarrassment, if you read the original version of my paper, the word modular does not appear anywhere in the paper. But that's what happens. Anyway, I found a solution to this is that it's delta ij. This is called the diagonal combination, which is sort of obvious once you realize this. But then I found others as well. And the question is, how many more are there? So this question was answered in 1987 by Capelli, Utzigson, and Zuber, who did this beautiful piece of work and showed that the classification of the solutions to this problem are very much like the ADE classification of simply laced the algebras, or the finite subgroups of SU2, or catastrophe theory. there are 2 infinite series and 3 exceptional cases. And then, just to kind of close the circle, people at Saclay constructed very simple lattice models, which are really simplifications of the Andrews-Baxter and Forrester models, where the degrees of freedom lie on the nodes of the ADE Deacon diagrams. And then you can argue, using these Coulomb Gas Methods, that these are in fact the ADE minimal CFTs. So the nice thing about modular invariance, it had already been shown by BPZ and SQS what scaling dimensions might appear, but modular invariance tells us which ones actually do appear. And so this was a very restricted solution to Wilson's challenge. One had a complete classification of the conformal field theories with C less than 1. Anyway, just to continue my personal journey, I'm aware that the time is going on, but I'll continue for a while longer. I finally got to meet the Russians, Zamolodchikov, Sasha Zamolodchikov, and Fateev and a bunch of others at a small joint meeting of the 2 academies, which are held in the depths of the Swedish forest, and it was a wonderful meeting. I just realized how smart these guys were, and Sasha had just derived his C theorem, which is this global statement about the irreversibility of renormalization group flows. There was a whole lot about off-critical integrable field theories, which was about to bear fruit when Sasha came up with his beautiful solution to the field theory of the IC model in a magnetic field. There was a lot of work to be done here, and I went back to Santa Barbara stimulated, and unfortunately at that time I had some very good students and postdocs, and we were able to write lots of papers. I also met up with some of the Russians in 1988 in Japan. Here's a picture. This is Sasha, this is me, and a few other well-known people. Rodney Baxter, Jimbo, Miwa, Palyavin, Itzikson, Lukianov, Iguchi, Olive, McCoy, and so on. It was a very interesting time. And there was also that year, which was 1988, there was a Lesush summer school with all kinds of lectures on conformal field theory and string theory. This is Sasha Polyakov in his usual informal dress, lecturing to a bunch of students outside, and it has to be said that a lot of these students who were there then are nowadays senior professors at their institutions. So let's see. Okay. So I'm at this point in around 1988. Conformal field theory just exploded as a subject. And so from now on, I'm going to be talking about things that I was involved with. And the first thing is boundary conformal field theory. And there's all kinds of reasons why one wants to study conformal field theories on manifolds with boundaries. And by about 1984, we understood from Renormalization Group calculations that for each bulk RG fixed point, for each bulk conformal field theory, there should exist different possible, quote, conformal boundary conditions, which themselves correspond to fixed points of the boundary renormalization group first. And actually, almost the first thing I did after I started to understand the BPZ paper was to extend their methods to a simply connected region with a boundary, which of course can be always conformally mapped to the half plane. And what I showed for the minimal models that BPZ were talking about is that I showed that the endpoint correlation functions, which in the half plane are going to depend on the complex coordinates z1 through zn, and also their complex conjugates, their images in the real axis. They obey the same PDEs as do the holomorphic two endpoint functions in the bulk. That doesn't mean that they're the same functions, but they obey the same equations. And this has huge implications because it means that the conformal boundary states and their data are basically determined by the same data as the bulk theory, somehow reinterpreted. However, quite how this worked was a puzzle, and it took me until 1989 to solve it. And as a side comment, this was before the days of the archive. I can't imagine a problem like that hanging around for 5 years and some bright postdoc not coming along and solving it. Anyway, that's what happened. So it really involved trying to understand the partition function on an annulus, which of course we get by having periodic boundary conditions on our rectangle, but having a boundary here with boundary conditions that we call A and B. And now we have a consistency condition, which is very much like the consistency condition in string theory between the open string and the closed string. So if we think about the Hamiltonian operating this way, we have a trace, but it's the Hamiltonian of the open string, which will depend on the boundary conditions A and B. On the other hand, if we think about it in the closed string sector, then it's not a trace anymore, but it's a matrix element between these boundary states. Whoops. So these boundaries, so the trace is easy. It's going to be a linear sum rather than a bilinear sum this time over Virasoro characters with some non-negative integer coefficients. But it took me a while to understand how to express these boundary states, and fortunately this paper of Ishibashi appeared, showing that if you take these so-called Ishibashi states, then these are going to satisfy the conformal boundary condition, which is a linear condition. And then the actual physical boundary states are going to be finite superpositions of these. And then this leads to some really interesting mathematics. Because the left-hand side is linear in these unknown coefficients, which have, however, to be non-negative integers. On the other hand, the right-hand side is quadratic in the coefficients of the states A and B when you express them in terms of the Ishibashi states. But the outcome is very beautiful. It tells you that the boundary states are classified by the same scheme that you use to classify the bulk operator content. And these non-negative integers are in fact an integer valued representation of what's called the fusion algebra that you'll probably hear a lot more about in the talk of Craig Moore. And interestingly enough, showing this identically involved using the Verlinde formula, which had also just appeared. An important new concept in this analysis was that one shouldn't just think about boundary conditions and local operators which can sit at the boundary, but in terms of boundary condition changing operators, that is, points on the boundary which are obviously in two dimensions are local objects at which the boundary condition changes, and they also correspond to highest weight Virasoro representations. And this is an example of the importance of studying in a conformal field theory in general, not just local observables, but also defects. So this kind of started people thinking about this. Okay, I'm going to spend a short amount of time now talking about an offshoot of this, which is random planar curves. So if you think about a two-dimensional lattice model, like the IC model, but its generalizations, the ON model and the Q-state pulse model, I'm not going to describe them in details, but instead of thinking about them in terms of the configuration of these spins, we can think of them in terms of their cluster boundaries. So within each cluster, the spins all point the same way. So in terms of these cluster boundaries, we have configurations of non-intersecting planar curves, which either form closed loops or they end on the boundary. And when they do that, there's typically a boundary condition changing operator there. And this is a very interesting point of view on 2D CFT because it introduces geometric observables, not just the energy density or the magnetization. For example, the probability that 2 points are on the same curve. This is a non-local observable, a bit like things that exist in the gauge theory. And in terms of a conformal field theory, they correspond to a non-unitary sector of the original conformal field theory. And it's usually a logarithmic one in the sense that L0 and L0 bar can't be diagonalized, but only brought to Jordan standard form. And when you go through that means that the correlation functions don't just behave as a power, but there are possible powers of the logarithm of the distance in the numerator. In the OM model or the Q-state pulse model, we can assign a weight n or square root of q to each closed loop. So the models actually make sense for non-integer values. We have a continuum of conformal field theories there. And there are interesting limits. Q goes to 1 gives percolation, n goes to 0 gives self-avoiding walks. In 1986, Duplantier and Saleur gave conjectures for the Vulcan boundaries. Scaling dimensions of what are called the n-like fields. That means n curves originate from a particular point. And the boundary fields in particular appear to correspond to Virasoro representations with null state. So their correlation function should satisfy BPZ type PDEs. And this led to the percolation crossing formula in 1991, which interestingly enough was the beginning of the archive. And this paper was my first submission to the archive. So in the percolation problem, this is really a probabilistic problem, but one imagines, for example, a square lattice where each edge is either open with probability p and closed with probability 1 minus p, and they're independently open or closed. And for small p, then we get clusters, small clusters of open sites, but there's a critical value of p, the percolation threshold, at which if one imagined the open links to be electrical conductors, one would first establish some kind of conductance across the whole system. In particular, one can ask for the probability that two opposite edges, the top and the bottom here, of a rectangle are connected by at least one open path. And if this rectangle is very long and squat, that probability is going to be close to 1. On the other hand, if it's very thin and very long in the vertical direction, that probability is going to be close to 0. So the answer is, what is it? Well, in '91, I received an inquiry from some Princeton mathematicians who had data that suggested this should be conformally invariant. That is, one can make conformal mappings of the rectangle, and it only depends on the modulus, or if one maps the rectangle to the upper half plane, it only depends on the cross ratio of the 4 points to which the corners are mapped. And I was able to argue that this is given by a 4-point function of boundary condition changing operators. And then I have guessed, I can prove this, that it's going to satisfy a second order BPZ type equation. And the solution is then just an ordinary hypergeometric function. And the marvelous thing, of course, is that I sent my solution to these people in Princeton, and it matched in a marvelous way their numerical data. So this is a highly non-trivial formula, and it intrigued mathematicians who then developed a whole theory of random planar curves called Schramm-Loebner evolution. Meanwhile, Stas Smirnov gave a direct proof of the crossing formula, and all this led to Fields medals for Werner in 2006 and Smirnov in 2010. Just one example of how conformal field theory has spun off ideas into mathematics. So I'm not going to talk about this. Although it's rather nice because it gives one a different interpretation of the central charge. Finally, I want to talk about conformal field theories as being theories of real physics. They're connected with string theory, which may or may not be real physics, but in condensed matter, one can actually have experimental realizations of 1 plus 1 dimensional conformal field theories. Now, although a lot of what I've said today was applying it to 2-dimensional classical critical behavior, and although it's easy to do numerical experiments on these, it's pretty hard to do detailed experimental verifications. In fact, helium is about the only real case where the systems are clean enough to do really detailed experimental work. But if one thinks about 1 plus 1 dimensions and this one-dimensional quantum systems, all sorts of applications, as long as the low energy dispersion relation is relativistic. And there are plenty of examples, one-dimensional, certain points in one-dimensional quantum antiferromagnets. Affleck talked about this early on, realizations of Kac-Moody algebras to interacting electrons in 1D, which was solved originally by Luttinger, but the conformal field theory analysis of this is interesting. Something I will talk a bit more about briefly. In ultra-cold atoms, one can confine them to one dimension, and there the low energy excitations correspond to a conformal field theory. If one talks about quantum Hall insulators, they're insulating in the bulk, but they have edge states, which are described by a 1 plus 1 dimensional chiral conformal field theory. That is, one only has either left movers or right movers, but not both. And the another beautiful example, which was discussed by Affleck and Ludwig, is if you think about the Kondo effect, where this is actually in 3 plus 1 dimensions. If you have a magnetic impurity in a sea of electrons, for example, do the electrons screen the impurity? What happens? And it's a classic example of strong coupling physics, which is described by a boundary conformal field theory. And the reason for this is, even though there are 3 space dimensions, it's only S-wave scattering of the electrons from the impurity, which is important. So S-wave, one is just talking about dependence on the radial coordinate, which runs from 0 to infinity. So it's just like a boundary 1 plus 1 dimensional conformal field theory. And they were able to take the general principles of what I'd done on boundary conformal field theory and apply it to the Kondo problem. I just briefly want to talk about more recent work I did on something called quantum quenches. So in a quantum quench, it's an old problem in quantum mechanics. If you start a system in a pure state, but you have a Hamiltonian H, which is going to be a conformal field theory Hamiltonian, and this is going to have an extensive energy. This pure state has an extensive energy above the ground state of your Hamiltonian. So one thing that you can do is to prepare the system in a ground state of some other Hamiltonian and instantaneously change a parameter so that the new Hamiltonian is H CFT. And then we initially have a density matrix here, which is the density matrix of a pure state. it evolves according to this Hamiltonian. And then we look at the reduced density matrix corresponding to a subsystem A by tracing out the rest of the system. So how does this depend upon B? Well, in a conformal field theory, we could solve this problem exactly because we know all the correlation functions, or at least we know enough about the correlation functions to solve this problem. So what we're essentially doing here is using a CFT as a laboratory in which we can do these kinds of thought experiment. So basically what we found was called thermalization, more technically pre-thermalization. If you think about the reduced density matrix at the time T, you can prove that it's exponentially close to the reduced density matrix of a Gibbs ensemble. So the system looks like it's at finite temperature. And technically it's a generalized Gibbs ensemble because a conformal field theory has an infinite number of conservation laws, but apart from that. And this happens in an amazingly fast time. It doesn't have to explore the whole of phase space or anything. In the time it takes for one excitation to cross the subsystem, it's pre-thermalized. And this is due to quantum interference. We can also compute the quantum entropy of this state, which was on something and what we find is that it increases linearly with the time, and then it saturates at the thermal entropy, which is of course extensive in the size of the subsystem. So then the nice thing about these calculations is it gives us insight into quantum many-body problems, which if we tried to simulate them on a digital computer would be impossible. But because the model is exactly solvable, we can do it. We could, of course, simulate them on a quantum computer, and that's an interesting question. So the interesting thing about these results is that they can all be interpreted or explained in terms of this quasi-particle picture in which the initial state serves as a source of locally entangled bell pairs, one going left, one going right. And these each quasi-particle propagates with the group velocity, which of course for a conformal field theory is just the speed of light or the speed of the excitations. But the interesting thing is you can take this quasi-particle picture and extend it beyond conformal field theory to systems which have a more complicated dispersion relation and so on. And it explains almost all the observed features of experimental data one can actually do these quantum quench experiments in cold atoms, because the interactions are sufficiently weak that the time scales are long enough so that one can resolve in time all these features that I'm talking about. And the interesting thing about our paper is that we coined the term quantum quench, which of course rolls off the tongue very easily, but you can gauge how many applications it's had by counting how many times it appears in archive abstract. So I'm sorry to have extended my time a little bit. Here's a few of the things that I have omitted, and certainly the most important one is the realization of Polyakhov's dream of the conformal bootstrapping high dimensions with improved analytic understanding of the contribution of the conformal blocks, and with much greater computational power, the number of things that have been done with the conformal bootstrap is amazing. Not just very tight bounds on the three-dimensional Ising model, but an important tool for investigating higher dimensional theories and finding new conformal field theories whose existence that we can expect. A couple of things here that we're probably going to hear about in Greg Moore's talk. The A theorem, which is a four-dimensional version of Zomologichov's A theorem, which I conjectured in 1988, fully expecting someone to find a counterexample. But then it was sort of proved in 2011 by Komogowski and Schwimmer, although I would still like to see a more direct version of the proof. Of course, the applications to conformal field theories, to string theories and brane theories, the whole subject of holography, early applications of Heinrich Polyakhov's homological to what happens when you put a conformal field theory on a fluctuating metric. Analytic results for these Liouville conformal field theories, which are the best study examples of irrational conformal field theories and logarithmic conformal field theories, which are very hard to classify. I mean, if you think about the problem of classifying ordinary conformal field theories, then a logarithmic ones are infinitely greater in number. So again, I apologize for having cut on, but I hope I've given you some flavor of how exciting this field was in the 1980s, and of course it's still going on. So thank you. And,
Professor Cardy, thank you very much. I wanted to open the floor for questions. I'll go first. I was actually wondering if you could say some more about the conformal bootstrap, and more broadly, if any of the you mentioned the prehistory of conformal field theory, and there were important works by Polyakov, by Migdal, in determining anomalous dimensions, and so on and so forth, and conformal invariance, and there was input from string theory in terms of world sheets and world sheet conformal field theory, and even though that wasn't as like that perspective wasn't as favored, but I guess I was wondering if that literature influenced your work later on in the 1980s.
Well, I myself have not worked on the conformal bootstrap. I mean, I certainly read the earlier papers of Polyakov and Migdal and so forth, and I think I came to the conclusion that at that point one had to make too many assumptions, or one had to truncate things too severely in order to be able to get believable answers out of it. And I think the more recent work of this since 2009 has really showed that one needed to go a lot further in order to get useful answers out of it. Any more questions?
Professor Cardy, thank you very much for the lecture. It's been an honor to attend your talk. Earlier in the lecture, you've briefly mentioned the correspondence between the region field theory and directed percolations.
Yeah.
Could you please elaborate on that and the role it played in our understanding of non-equilibrium phenomena?
Well, let's see. Region field theory was an attempt to sum up all the contributions of the Pomeron in terms of Reggie poles and Reggie cuts and so forth, and to somehow sum up the whole series. In region field theory, it looks like a non-relativistic quantum field theory with a purely imaginary bicubed coupling. But the physical interpretation there of what appears as time is in fact rapidity in the language of high energy physics, and the physical interpretation of space is impact parameter. So if one then takes that same phi cubed non-relativistic field theory and interprets this as real time and space as being real space. This describes a kind of a non-equilibrium process, which actually had been studied for a long time by people in probability theory. And what I and a couple of other people were able to show was that understanding what the critical behavior of region field theory, one was able to understand the critical behavior of this non-equilibrium process, which, for example, models the spread of infectious diseases, though it's a little bit oversimplified to describe a realistic case, but there has been recent work to show that directed percolation describes the transition to turbulent flow. And there one can do real experiments and one can confirm the values of the critical exponents that were calculated a long time ago in region field theory. I hope that answers your.
It did. Thank you. Thank you very much.
If there aren't any more questions, we'll be ending the talk here.
Hello?
Oh, hello. Yeah, I think since there aren't any more questions, we'll be ending the talk here. Thank you very much.
Oh, thank you.